In this lesson, we're going to be looking at systems of equations with two variables. We focused on this a little bit in Module 1, but we looked at them graphically instead. So in Module 1, we saw a graph and we looked for any intersection points. And that point, the x-y coordinate, represents the actual solution to the system. In our case, this one system that's graphed intersects at one point, so it has one solution. We would call this a consistent and independent system. In the second graph, you see two lines that are parallel. So these things are never going to intersect, which means that they have no solution for this system. When something has no solution, we call that an inconsistent system. And in the third graph, it's a little bit harder to see with this picture. I didn't print it in color, but we have one line that was in red and then another line that's dotted and it was in blue. So those two things are on top of each other. And what that's just representing is that those two equations actually are the same and they'll have infinitely many solutions. So infinitely many solutions goes in that bottom blank. But the type of system that we're working with is called a dependent system. That's because our solution depends on what we choose for our x or our y. Now, if we want to solve these algebraically, we have two methods that we can look at. One of them is going to be the substitution method. In this one, we're going to be solving one of the equations for a variable and then substituting that expression into the other equation. To do this, I would choose a variable that doesn't have a lot around it. When I look at this x, it has a coefficient of 1. And so there's not a lot that I'm going to need to do to be able to get x by itself. So that's what I'm going to start out with, is take this equation and move the 3y to the other side so that x is by itself. That would make this x is equal to a positive 3y plus 1. We take that 3y plus 1 and that can be substituted into the other equation. You don't plug it back into the same equation you just solved for. It always goes back into the other equation. So this was 3x. Instead of writing x, we're replacing it. And so this whole expression goes in place here. And we make that 3y plus 1. We have minus 8y equals 5. This is similar to what we did in polynomial modeling, where we had to solve for a variable and plug it in so that now we have one equation with one variable. If I distribute, I get 9y plus 3 minus 8y equals 5. Solving that, we can combine like terms to get 1y plus 3 equal to 5, which means if I subtract 3, y equals 2. So that's the y value, but we still need the x part of the solution. You can plug it into any of these equations that we started out with, but we had a solution where it was x is equal to 3y plus 1. So let's plug it back into there. So I'm going to take that y and plug it into this y, which means that x is equal to 3 times 2 plus 1. 3 times 2 is 6, plus 1 is 7. So our solution is when x is 7 and y is 2. We write that solution as an ordered pair, 7, 2. And we can check our solution just by plugging it back in. So this should be a unique solution when I plug it in here and say if x is 7, minus 3 times y was 2, I should get 1, and we do. If I plug it into the bottom equation, 3 times 7 minus 8 times 2 should equal 5, and it does. So this solution works for both equations. Now the elimination method is still trying to eliminate a variable so we can get down to one variable. But we want to organize it. So we're going to organize the system with all variables on one side and the constant on the other side. We do want to make sure that the variables are lining up. So all the x's are kind of in a column, all the y's are in a column, and then equals to the constant. We can use a multiplier, sometimes called a scalar, to create equal coefficients on opposite signs with one of the variables. So let's see what that looks like. But first, when we look at this equation, I need it to where all of the variables are on the left and the constants are on the right. So this first equation has x, y equals the constant. To get it in the same way, I want the second equation to move that 2x to the other side. So that would say, let's just move this around. 2x goes to the left, that makes it positive 2x. Y is already on the left, so it's just plus 6y equals, and I need to move that 2, that constant, over to the right. When I do that, it becomes a negative 2. So now our system has all of the x's in a column, all the y's in a column, and the constants on its own column. We're going to use a scalar or a multiplier to create equal but opposite signed coefficients for one of the variables. So when I'm thinking about this, 12x and 2x, I could get them to be 12x and negative 12x, or we could go to our y's and I can get this to be, this is already a 6y, so I can get the top to be a negative 6y. So you just choose whichever variable you want to eliminate first by using this multiplier method. So what I'm going to do is scale that top equation and multiply it by negative 6. What that's going to do when I distribute is give me a negative 6y. So negative 6 times 12 should be negative 72x. Negative 6 times y is negative 6y. And then negative 6 times 23. And use your calculator. You don't have to do all this in your head. But I get negative 138. The bottom one I don't have to change at all. So it's going to be 2x plus 6y equals negative 2. And we did that, so what we can do is add the equations together. We're just going to add straight down to get negative 72x plus 2 is negative 70x. Negative 6y plus 6y is 0. We wanted to eliminate a variable, that's what we just did. And then negative 138 and minus 2 is going to be negative 140. Now we have an equation with just one variable. We solve for x by dividing by negative 70. So x equals positive 2. Now we know what one of the variables are. If we take that x and plug it back in, I can plug it into any of the equations that we had. So let's plug it back into this 12x plus y equals 23. So 12 times x, which is 2, plus y equals 23. Make that 24 plus y equals 23. And we solve for y. So y equals negative 1 when we subtract 24 over. Now I know what x is and what y is. We can take that and write our solution as our point 2, negative 1. And if we were to graph both of these equations, we would see that they do intersect this particular point. But if you only name one of the values, you haven't completed your system. All right. So for number 3 and 4, you can solve using any method you want. If you want to pause the video and try to solve, you can go ahead and do that, or you can work it through with me. All right, so when I look at this one, I see that everything's kind of out of order. So I'm going to put this to where it's all the x's and the y's on the same side and our constants on the other. But actually, I don't really need to do anything to the first one. I'm just going to rewrite it where it's x plus 12y equals negative 14 here. So I didn't have to rearrange anything. But the other one, we've got a 10x on this side. Let's move the 6y to the right. So that means I'd have 10x plus 6y equals, if I move the 6y over, then I still have the negative 26 over there. So that's one way to rearrange this. You could have solved this using substitution if you wanted to solve for x and then substitute in. Either way is fine. But if I use elimination, we need to eliminate one of the variables. So I'm going to choose my x's to eliminate. And I can do that by multiplying the x's by negative 10. Or just that top x by negative 10. So if I do this here and distribute, that would give me a negative 10x. Negative times 12 is negative 120y. And negative times a negative is now positive 140. But the second equation, I don't have to manipulate at all because I've already got something that's going to eliminate my x's. So now those are going to disappear when I add straight down. If I add these together, negative 120 plus 6 is going to be negative 114. And then 140 minus 26 gives us 114. So when you divide by negative 114, I end up as y is negative 1. I found out what y is. We need to plug in to find out the x value. You can plug it into any of these equations. So if x plus 12 times y, which is negative 1, is equal to negative 14, that would simplify down to just x minus 12 equals negative 14. Then I add 12 to both sides and get negative 2. So our x value is negative 2, our y value is negative 1. Let's just write that as our point. Negative 2, negative 1. All right, example 4 still has some things that are out of order. So I'm just going to rewrite this 6x minus 12y equals 5. That first one's fine. But if I want all the x's and all the y's together, then I might have to manipulate this and move it around some. So I can move the constant to the left, and I would have a 3x minus 6y equals, and if I move that over to the left, it'd be equal to a positive 3. But again, you could have moved all of your x's and your y's to the left. Either one is fine. What I see is that I'm going to have to manipulate this. If I want them to be opposite signs, I'm going to have to multiply by a negative somehow. So let's say I take the second equation, multiply by a negative 2. That would give me a negative 6x. But negative 2 times negative 6 is positive 12. And negative 2 times 3 is negative 6. The top equation, I didn't have to manipulate at all. What we see when we add straight down is that the x's cancel out, but so do the y's. So we get down to 0 equals, and then 5 minus 6 is negative 1. Well, 0 does not equal -1. This is not true. We can write not equal to. So we got down to where all of the variables have eliminated. We have no solution. Okay. And then example 5, you can choose again whichever method you want. I just tend to like elimination a little bit better. And it's already kind of lined up. If you look at it, x's are on top, y's, and then our constants. So 6x and -10x, there's not a really good way to multiply to get those to cancel yet. And 3 and 5, still not a good way. So what happens is we have to actually multiply both of them, and that's fine. So I'm just going to rewrite this for a second so that I have room to show you. So we think about what is a common multiple for either one of the variables. Thinking about 3 and 5, a common multiple is 15. So I would need to get them both to say 15, which means I would have to multiply the top one by 5. And I want one to be a positive 15 and another to be a negative 15. Well, that one's already going to be a positive. This is already negative, so I can multiply it by 3. And then we see what we end up getting. So 5 times 6x is 30x. 5 times 3y is 15y. And 5 times -12 is -60. Then we multiply again. So -30x, -15y, and then 3 times 20 is +60. If you add straight down, the x's cancel out, so do the y's, and then 60 and -60 is 0 as well. So we do get 0 equal to 0, and this is one of those special cases because it was an infinitely many solution one. All right, so infinitely many solutions. If it comes down to 0 equals 0, that's an infinitely many automatically. If it was 0 equals some other number, then that was the no solution. So when we have an infinitely many solutions example, we're actually going to write our solution in a different way. So it says that our final answer should be written in this way, where x is in terms of our y, and y is just any real number for y. So what I would do is take one of our equations. Let's say I have the 6x plus 3y equals -12. We want to solve for x so that it is in terms of y. So let's get x by itself. I'd subtract the 3y, so it's -3y minus 12, and then divide by 6. So -3 divided by 6 is going to be -1/2 y, and -12 divided by 6 is -2. So x would be -1/2 minus 2. We would write this in this way, where x is -1/2 y minus 2, and then our y value is just y. And it's a little bit different. We haven't seen that type of example before, but that's the notation that we would write this as. So I guess I should write this here. The answer to the system is -1/2 y minus 2, comma y. And this is known as that dependent system. All right, so for 1 and 2, pause and try these out completely on your own, and then when you're ready, you can pick back up the video to see if you did it correctly. All right, so I would multiply this top one by -6 so that I can eliminate my y's. It gives me a positive 30x, -6y. And then 6 times 24 is 144. So I get a -144. And then 3x plus 6y equals -21. I don't need to change that one. So the y is canceled out. We got 33x, -144, plus a -21 is -165. We take that and divide by 33. And we get -5 for x. Once we know x, we can plug it back in for y. So -5 times x, which is also -5, plus y equals 24. So that's 25 plus y equals 24, and we subtract 25. 24 minus 25 is -1. So our solution here would be -5, -1. And then the second example here that you had, you can multiply either one of these, it doesn't matter, but I'm going to multiply the bottom one by -2. So I would end up with a -8x, -2y, and -28. The top one we don't need to multiply at all. When you add straight down, we see that the x's cancel out, the y's cancel out, and really the last ones also cancel out. So we do get 0 equal to 0. So this is automatically one of those dependent systems. We have to take one of the equations and solve for x. So I would have 4x equals -y plus 14, and -1/4 y plus 14 divided by 4 would simplify down to 7/2. So our solution would say -1/4 y plus 7/2, comma, y. Okay. The last part of this video is just about the systems with two variables as an application. In this, we have the admission fee to a park is $1.50 per child and $4 per adult. If 2,200 people enter the park and the total fees were $5,050, how many children and how many adults were there? So basically we have two different variables. You want to define what your variables are going to be. We can let A be our adults and C be our children. You could also be X and Y, whatever makes you happy and makes sense. But you do want to label them. If you chose X and Y, make sure that you label so that you know X you chose for adults and Y you chose for children, or vice versa. So the admissions fee is $1.50 per child and $4 per adult. I know that I'm going to make $1.50 for every child's ticket that we sold, plus $4 for every adult ticket that we sold. Well, that's going to equal the total amount of money that we got. So when we sold 2,200 tickets, or 2,200 people came, we made $5,050. That $5,050 is going to go with all the other money equation, so 5,050. But because this is a system, we need two equations. We've got one, the other comes from this 2,200 people. All of the children plus all of the adults together should make up the 2,200 people in the park. So you have to set up the equation, then you can decide what method you want to actually solve this by. So let's see, I'm going to multiply by a negative 150. So when I multiply this, this would say negative 150, 1.50, C minus 1.5, 0, A equals, and I have to do a little bit of multiplication here. So 2,200 times negative 1.5 is negative 3,300. Then the top equation didn't change. I could have multiplied by negative 4 if I wanted to pick a nicer one. It doesn't really matter. But 1.5 C plus 4A equals 5,050. When we add straight down, we see that the children cancel out. Now we have the adults, so 4 plus negative 1.5 gives us 2.5. A equals, and then 50 minus 3,300 is 1,750. We divide by 2.5, so 1,750 divided by 2.5 is 700. This means that they sold 700 adult tickets, or 700 adults came. Now we need to find out how many children were there. So C plus A, 700, should equal 2,200. And we can subtract. So 2,200 minus 700 is 1,500. Now we can just answer the original question. So how many children and how many adults entered the park? There were 1,500 children and 700 adults at the park. All right, example 2. We have a boat that on a river that travels downstream between 2 points 20 miles apart in 1 hour. It makes its return trip against the current, and it takes 2.5 hours. What is the speed of the boat and what is the speed of the current? So basically it's given us our two variables in that last question. What is the speed of the boat? Well, X is going to be our speed of the boat. And Y is going to represent our speed of the current. Now these problems, it can be tricky. I remember I used to hate these until I learned that there was a way to organize it a little bit better. But what we see is this speed is a rate. In our case, it's miles per hour. Since we're traveling 20 miles apart and 1 hour, we can use our rate. And so if you recognize that this is really a distance equals rate times time kind of problem, that's our formula. So distance equals our rate times the time. I can organize this information based off of that one equation. So think back to what it means when you're traveling downstream versus when you're traveling upstream against the current. If you're going with the current downstream, you should be going faster because the current is helping you along with the speed of the boat. So we're going to travel 20 miles no matter what, because it's the distance between the 2 points. But the rate at which we travel is going to change, because when we're going downstream, that rate is the speed plus the current. So our rate would say X plus Y and the amount of time that it took. So in our case, it took 1 hour. The other way we're still traveling 20 miles, but we're going upstream against the current. So this was our downstream. Let's write this out here. Downstream. And this is upstream. We still travel 20 miles, but the current's working against us. When you go upstream, you're going against the current. So now it would say you have the speed of the boat, but you have to subtract the speed of the current because it's working against us, which makes this take longer. So we're going to travel, and it takes 2.5 hours. And there's our equation. You could work through these things and distribute. Distributing a 1 isn't really going to do much, but you can distribute the 2.5. One other way to work with that equation, if you have x minus y times 2.5 equals 20, a valid step is to divide by 2.5. So that would just give me, let's divide that out, x minus y equals whatever 20 divided by 2.5 is. So that's 8, which is the same equation just without the 2.5 there. So I have these two equations, x plus y equals 20 from the first one, and the second one gave me x minus y equals 8. I like that one just a little bit better because when you eliminate these, it makes it come out nicely to be 2x equals 28. So then x is equal to 14. We know what x is, but we still need to find out what y is. So I'm going to take that first equation, x plus y equals 20, and substitute this back in here. So 14 plus y equals 20, which means y equals 6. Now with word problems, like I said, these variables don't mean anything to us unless we have defined them. So we want to just interpret what this means. The speed of the boat is x. We chose that it was going to be x, so then it is 14 miles per hour. And then the speed of the current is 6 miles per hour.